SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of Thermal Engineering Basic and Applied, and today we shall discuss about the limitation of a simple float type carburetor, and then finally we will solve two problems from the carburation part. Now, if we try to recall, in the last class we have discussed about the operation of the simple float type carburetor, and we could establish the expression of mass flow rate of fuel and mass flow rate of air. From these expressions we could write the ratio of fuel air mixture. Now, we had seen that if we try to superimpose the mass flow rate of fuel, the ratio of mass flow rate of fuel and mass flow rate of air for varying pressure difference, we had seen that it is increasing the ratio of fuel and air or air fuel ratio is increasing linearly with a change in pressure drop, and by plotting that variation in the regimes of operation of internal combustion engine, we had seen that if a carburetor is designed for the satisfactory operation of engine in its idling condition, the same carburetor will provide fuel air ratio to the engine at the cruising zone or also during power zone, which is far too rich mixture and that is not needed. So, let us draw that schematic, let us draw that variation, and from there you can discuss again today. So, if this is the pressure difference P A minus P B, this is as good as throttle opening area, because by tuning this particular pressure drop, we can vary the flow rate or fuel air ratio which would be drawn into the cylinder. And if this is the fuel air ratio and say this is fuel air stoichiometric, and if we draw three different regimes of internal combustion engine operation, we can see these are the three different regimes. So, this is A, this is B, this is C, this is D, and we had seen in the last class this AB regime is the idling zone, BC is the cruising zone, and CD is the power. power zone. So, these three distinct regimes we could identify, and the required fuel air ratio for these three different regimes we can see from this plot. Now, if we try to superimpose the fuel air, so this is the fuel air ratio that is needed by an engine for its operation during three distinct regimes. Now, this is the requirement to the engine, but that fuel air should be fuel air ratio or fuel air mixture to be supplied by a carburetor to the engine, and if we try to draw the characteristic curve of the carburation. So, if we just draw, we know that initial pressure difference is needed, say if this is the initial pressure drop, so this initial pressure drop needed for the flow of fuel. So, the fuel will start flowing from float chamber to the discharging point through that orifice, provided this initial pressure drop is there. So, this is required to overcome the frictional losses as well as the surface tension effect, by overcoming the surface tension effect. Now, if we try to draw the fuel air ratio that would be supplied by a carburetor. So, this is case 1. Okay. We also can draw another curve like this. So, this is case 2, case 3 rather, and if we draw another curve, say this is case 2. So, what we can see, if this particular carburetor, which is again a simple float type carburetor, is designed to supply fuel air ratio for the satisfactory operation during power zone, we can see using the same carburetor the fuel air ratio to be supplied to the engine during idling zone is far too lean. So, it is not suitable. Maybe the same carburetor is suitable for the adequate fuel air ratio as needed by the engine during the power zone, but the carburetor is not capable to supply the required fuel air ratio during idling zone. So, it is not I can say it is one of the limitations. Similarly, if we somehow design the carburetor to supply adequate fuel air ratio during idling zone, if we look at case 3, then you can see the fuel air ratio to be supplied during cruising zone as well as during idling zone, during power zone is far too rich mixture. So, it is unnecessary wastage of fuel air ratio. So, that means we can see there are a few limitations of the simple float type carburetor, and now we need to list down what are the several drawbacks associated with the operation of a simple float type carburetor, and if we need to overcome those drawbacks, we need to modify the design of simple carburetor. So, now we shall discuss about the limitation. Of a simple carburetor, right. So, that we can write now. Basically, what we can see, we can write that number 1, at no loads, right, the mixture becomes linear but engine requires the mixture to be enriched at no loads. So, this is number 1. Which one this? So, you now look at case 3. So, maybe this carburetor is providing adequate fuel air ratio during power zone, but using same carburetor the fuel air ratio to be supplied during idling zone is not adequate. So, this is what we had written. That means, at no load idling zone engine is running in this zone, that means engine is not, we are not extracting any load, any power from the engine. So, there is no load as such. So, and during that condition that fuel air ratio to be supplied by a simple flow type carburetor is not adequate. So, it is the the carburetor is unable to meet the demand of the engine. So, that is what I had written. Okay. Number 2. Number 2 is at intermediate load, the mixture equivalence ratio, the mixture equivalence ratio, which is this equivalence ratio I am underlining, which is fuel air actual divided by fuel air stoichiometric. Okay. So, the equivalence ratio, that is the I had written over here, increases slightly. So, equivalence ratio, this is the equivalence ratio, increases slightly, okay, as the airflow increases. And but engine requires almost constant equivalence ratio. So, this is very important. Let us go back to the previous slide. So, this is intermediate stage of operation, that is the cruising zone. Most of the time engine should run in this zone, that is the most economy, I mean we get best economy of the fuel. So, basically that this is the zone in which engine should run most of the time, and you can see that whether the carburetor is designed or carburetor is adjusted to supply satisfactory fuel air ratio either during idling zone or during power zone. In both cases we can see the equivalence ratio, that is the fuel air actual by the fuel air stoichiometric, which is slightly higher than the requirement, right. And we can see that if we increase the pressure drop, so airflow will increase, as a result of which the equivalence ratio is not exactly constant and which is supposed to be. You can see that the blue line is almost lying on the yellow line. So, these two lines are coinciding, that means this equivalence ratio is almost 1. So, at this particular stage equivalence ratio is 1, but what we can see in either in case 1 or case 2 or case 3 the equivalence ratio is increasing. So, this is again one of the limitations of the simple float type carburetor. Okay. So, if we go to the next slide, then number 3 is elementary carburetor. The elementary carburetor cannot compensate the transient phenomena okay. So, the elementary carburetor cannot compensate the transient phenomena in the intake manifold, okay, nor it can. So, I can write neither cannot compensate the transient phenomena in the intake manifold, nor can enrich the mixture during engine starting and warm up. So, this is very important. You know that if we go back to the previous slide, idling zone, this is the zone in which engine runs either during starting or warm up. So, basically no load is extracted, there is no load, but still engine is running and we need higher failure or rich failure ratio. We can see that higher failure ratio. We had discussed that we need to supply more amount of fuel. Now, what we can see that this elementary carburetor neither can compensate the transient phenomena in the intake manifold, nor can enrich the mixture during engine starting and warm up. Try to understand, if we go back to the previous slide, whether even if we can adjust the carburetor to supply the failure ratio, which is though not perfect, but satisfactory, I mean the engines can be supplied failure ratio, though that particular failure ratio is not perfect for the operation of engine during idling zone, but still it can run. But if we can say that even if we run engine following case 3, I mean if we design the carburetor in such a way that it is running following this curve that is shown in case 3, in that case it cannot enrich by supplying more amount of fuel that is needed during warm up or starting. So, this is one of the limitation. Now, issue is if these are the limitation, so perhaps while someone is trying to design the modern carburetor, the designer must consider all these issues, and these issues should be addressed by suitably modifying the design of a simple float type carburetor. So, the last point let me write that limitations, that is number 4. 4 is the elementary carburetor cannot adjust, which is very important point, but that point that particular objective is not getting satisfied by a simple float type carburetor. So, cannot adjust to a change or changes, simply changes in ambient air density is due to, which is primarily due to change or changes in altitude. So, this is again an important drawback. If the engine is attaining certain height with a change in altitude, ambient air density will change. If that is the change, then perhaps engine needs the required mass flow of air for its efficient operation, but simple carburetor cannot adjust that due to changes in ambient air condition. So, this particular aspect also should be taken into account while modern carburetors are designed. So, now I am not going to write again the objectives of the modern carburetor design. So, basically if we can understand the limitations, and these limitations should be addressed while a designer is designing a modern carburetor. Okay. So, now with this, now let us move to solve two problems from this particular module, that is carburation. And the first problem that I would like to solve is from the stoichiometric air fuel ratio. While we have discussed about the stoichiometric or chemically correct air fuel ratio, we had discussed that chemically correct air fuel ratio, a stoichiometric air fuel ratio is the chemically correct air fuel ratio. So, if we know the composition of the fuel, basically hydrocarbon, and then to burn that fuel we need adequate air. Why we need adequate air? Because the amount of oxygen needed for the complete combustion of the fuel, that oxygen will come from the air being supplied to the engine. So, what is the actual amount of air that we need per cycle to be supplied to the engine for the efficient combustion, that is very important. If we can figure out, that would be the stoichiometric air fuel ratio. Now, that means per kg of fuel, if we can calculate what is the amount of air needed. Now, let us solve this problem. So, this problem, let us first read the problem statement. A hydrocarbon fuel is expressed as CXHY. So, it is a generic form. Instead of writing C8H18 or any other formula, it is better to write in a generic form. So, a hydrocarbon fuel is expressed as CXHY. Write the stoichiometric equation for this fuel. That means, we need to write the chemical reaction with oxygen. From there we can calculate what would be the amount of air needed to be supplied by the carburetor to the engine. The fuel contains 84% by mass of carbon and 60% by mass of hydrogen. Determine the stoichiometric air fuel ratio. So, first what we need to write? We need to write the stoichiometric equation. So, the equation, chemically balanced equation, and then by writing that particular equation we can quantify the amount of air needed to burn that fuel in an efficient manner, that is the combustion should be efficient. So, let us solve this problem first. So, that fuel formula is given CXHY. So, fuel is CXHY. Now, if we try to write the balance equation, so CXHY, we are supplying air because the oxygen present in the air will help to burn that fuel. Other constituents present in the air will create several combustion gases, NOx, SO2, etc. CO2. Now, if we write the equation, then it is what we can write, x CO2 plus y by 2 H2O. So, this is the chemical reaction. I had written considering the carbon and hydrogen which is there in the left hand side. So, now we can complete the amount of oxygen needed. So, what is the amount of oxygen needed? We know that CO2 will be produced, water vapor will be there, plus this reaction is exothermic. So, this is heat that will generate. So, now if we write it, so this is O2. So, it would be x plus y by 4, very simple. Now, this is the stoichiometric equation of this fuel, right. So, this is the stoichiometric equation, very easy. Stoichiometric equation of the fuel. Okay. So, now next it is given that fuel contains 84% by mass of carbon and 16% by mass of the hydrogen. So, writing the stoichiometric equation of this particular fuel, what we can do is, from this particular equation we can write mass of fuel equal to 12x plus y. So, this is the mass of fuel, right, and so this is stoichiometric, and what we can write, this is the mass of fuel, and it is given fuel contains 84% by mass of carbon and 60% by mass of hydrogen. That means, this 12x by total mass 12x plus y, that is 0.84, and we also can write y by 12x plus y, that equal to 0.16 mass. So, if this is the total mass and the mass of carbon is, that is given in percentage, that is 0.84. From these two expression we can write, so from these two expression we can write 12x by y equal to 0.84 by 0.16, that means y equal to 16x by 7. So, that we can write simply. So, if we go to the next page, then we can write the equation again. We can write the equation, that is Cx Hy plus x plus y upon 4 plus O2. So, this is x plus y upon 4, and we had written y equal to 16x by 7, and if we write in terms of, so if we go back, we have written y equal to 16x by 7. So, if we write the value of y in this equation, then we can write this would be 11x by 7, right, that is x plus y upon 4. So, that is x plus 4x by 7. So, this should be equal to x plus 4x by 7, okay, and that is equal to x CO2 plus y upon 2 H2O plus definitely some amount of heat that we are going to getting. Now, we should not write y, because this is, we need to write in terms of x. So, if we write x equal to we have written 16x by 7. So, y by 2 would be equal to 8x by 7, 8x by 7. And what we can write? So, what we can do? We know that 23.2% oxygen is present. That means, if we consider 1 kg of air, so 0.232 kg of oxygen is available in 1 kg of air. Okay? That means, so 1 kg of oxygen available in 1 upon 0.232 kg of air, right. So, that means air by fuel stoichiometric is equal to that equal to let me write over here. So, I can write this is equal to, right. What is fuel? Fuel is 12x plus y. So, fuel, let me write here the fuel. So, fuel is 12x plus y. Now, what about y? So, 12x plus 16x by 7, and that should be 100x by 7. What about air? So, this is fuel, we can write 100x by 7. And what about air? See, 11x by 7 gram oxygen is needed per kg of fuel. So, this 11x by 7 into 32 into 1 by 0.232. So, 11x by 7 into 32, that much oxygen is needed to burn this much amount of fuel, that is 100x by 7. So, this 12x, so that is, if I write in, so basically this is 12x plus y, okay, and this is 11x 7 into 32, right. So, this much amount of oxygen is needed to burn this much amount of fuel. So, basically what is the air fuel stoichiometric? Amount of air, that is this, and this much amount of oxygen will be available multiplied by this factor kg of air. So, if we do this, we are getting it 15.17. So, this is the answer, right. So, the air fuel ratio, air fuel stoichiometrics is equal to 15.17. So, this is the process of calculating the stoichiometric equation as well as stoichiometric air fuel ratio. So, another problem that we will solve today is again from the carburetor, and in the last a few classes we had tried to establish the expression of mass flow rate of fuel and mass flow rate of air. Now, the most important part of a simple flow type carburetor that we had seen is the venturi, because a proper design of the venturi is needed to ensure that the pressure drop that would be there at that particular section should be good enough to ensure that a flow of fuel from float chamber to that particular fuel discharging point can be initiated. And that is why I would like to solve another problem wherein we can calculate the venturi diameter as well as the diameter of the orifice tube. So, let us this is the problem. So, let us first read out the problem statement. a simple jet carburetor is required to supply 6 kg of air per minute, it is given, that is mass flow rate of air it is given, and 0.45 kg of fuel per minute. The fuel density is 740 kg per meter cube, rho f is given, ambient conditions, that is pressure is given 0.1 megapascal, temperature is 300 degree Kelvin. Calculate the throat diameter of the venturi for a flow velocity of 92 meter per second. As I told that the pressure drop at the venturi, pressure drop of air should be such that the adequate flow velocity can be maintained, and the coefficient of discharge is given 0.8, it should be CDA, it is written CA. So, if I mark here, so this is actually should be CDA, CDA is equal to 0.8. If the pressure drop across the fuel metering orifice is 25% of that at the venturi, calculate the fuel orifice diameter if the coefficient of discharge of fuel is 0.6. So, CDF is given. So, what we need to do? We need to first draw the geometry, and from there we will try to solve this problem. So, if we try to write, so this is the solution. So, let us first draw the geometry. So, this is, I am not going to draw again, but just for the problem we had drawn, this is the orifice tube, fuel discharging tube, and this is the fuel discharging point, and this is the venturi, and if we give the section, this is BB and this is section AA. Okay. So, this is air is coming from top and this is fuel. So, this is fuel. So, what we can do, we can write down the data which we can read from the problem statement, that is mass flow rate of air, that is 6 kg per minute, mass flow rate of fuel, that is 0.4 kg per minute, density of fuel, that is 740 kg per meter cube, okay. And we need the flow velocity of 92 meter per second. Calculate the throat diameter of the venturi for a flow velocity of air definitely. So, this is flow velocity of, this is air flow velocity, air velocity. So, basically CB 92 meter per second. So, this is the velocity of air at section BB 92 meter per second, and CDA, that is 0.8, CD comma F, that is 0.96, 0.6. So, these are given. Most importantly, PA is given, that is 0.1 megapascal, and TA equal to 300 Kelvin. So, these are the data that we can get from the problem statement. Okay. So, if we try to solve it, just try to recall what did we do. We had applied steady flow energy equation between section A and section BB to calculate the velocity of air at section BB. So, BB section, which is at the venturi, I mean there in that at that section venturi is provided, right. So, if we apply that steady flow energy equation, we can write H B plus Cv square by 2 that equal to Ha, because Ca is much less than Cb, right. So, from there we can write Cb that is equal to twice Ha minus Hb under root. Okay. So, and this Cb, and we can write 2 Cp into Ta minus Tb. We have assumed that this is the flow of an ideal gas and the process is modeled by an isentropic process. The flow is modeled by an isentropic process. So, this is basically this is velocity of air at venturi or section BB. Okay. So, you know that if we write one step further, we can write it that particular we did it in the last class 2 Cp Ta into 1 minus Pb by Pa power gamma minus 1 upon gamma. So, this is total power half. So, Cb is given, that Cb is given. Now, this is the velocity that we are calculating using the flow of an ideal gas and the flow is modeled by an isentropic process. So, definitely the flow velocity of air at section BB is not the actual flow velocity, but what we need, if we go back to the problem statement, we need to have the actual flow velocity of 92 meter per second, right. So, this is the velocity that we need actual, but the velocity expression that we have here is the expression for the ideal velocity. So, now I am writing this is the ideal flow velocity. Okay. So, if we now write Cb actual equal to Cb ideal multiplied by Cda. So, this is, that means we can write 92 divided by 0.8, because 92 is the actual flow velocity that we need. So, actual velocity we need is 92 meter per second. If I divide by Cda, that is equal to Cb ideal, and that if we write 2 into 1.005 into 300, okay, and into 10 cube into 1 minus Pa Pb by Pa power gamma minus 1 upon gamma. Okay. So, this is gamma. So, this is the expression. Okay. So, we can write Pb minus Pa. So, from there we can write that if we calculate, we are getting Pa equal to 0.1 megapascal. We have multiplied by 10 cube. So, we are writing here Pb will be equal to 0.0925 megapascal. So, you can clearly see that there is a drop in pressure from 0.1 megapascal to 0.09. So, there is one order less, and accounting for this drop in pressure, we can have a flow of fuel from float chamber to the discharging point. So, if you just calculate, you will be getting this value. So, this is the PV. Okay. Now, knowing this particular PV, if we apply continuity equation at the venturi throat. So, if we apply the continuity equation mass flow rate at the venturi throat, we can write m dot air, that is equal to density of air at section BB, velocity of air at section BB into area. So, this is section BB. So, this is the actual velocity at section BB, and this is cross sectional area at section BB. So, if we write it, you know, this is given 6 kg per minute. So, that is 6 by 60 kg per second. Okay. And from this particular expression, we can write 6 by 60 equal to, you know, this density, let me write, because PB by PA equal to rho B by rho A power gamma. Okay. So, what we can write, rho A equal to PA by RTA. PA is known 0.1 MPa, TA is given 300 degree Kelvin. If I put the value of R, so we can write the expression that is equal to 1.16 kg per meter cube. And if we know the rho A using this expression, that is again let me tell you, because we have assumed that the flow of air is modeled as the flow of an ideal gas, and the flow is isentropic, flow is modeled by an isentropic process. So, now issue is, if we know issue is rho A, so rho A we could calculate, because PA and TA these are given. Now, what we can write, PB is PB that we have calculated, right, from the previous expression. So, from the previous slide we can see we have calculated PB, right. So, if we have calculated PB, if we plug in the value of PB, PA and rho A, we can find out rho B air at section BB, and that is 1.097 kg per meter cube. So, this is 6 by 60 equal to 1.097 into 92, that is the actual, because we are going to consider actual velocity of air at section BB multiplied by pi by 4 into dB square. So, this is the diameter this is the diameter of throat of the venturi. So, this is the final expression, and from this expression we can easily calculate what would be the diameter of throat at venturi. What would be the diameter? From this we can calculate dV will be equal to 35.52 millimeter. So, this is the answer. So, the diameter of throat of the venturi is 35.52 millimeter. So, if we go back to the problem statement, so the first statement, first problem, first objective was to calculate the throat diameter of the venturi. So, if we mark here, that is we have already calculated. Next is we need to know, because this is the flow of air. So, for such a flow of air, what would be the flow of fuel, and that is also given. Now, if we need to have a continuous flow of fuel from the float chamber to the fuel discharging point, what would be the diameter of the venturi, diameter of the orifice. So, fuel metering orifice, that we need to calculate. So, now second part of this problem, that part is also very important. So, let me draw again the schematic. So, this is the okay. So, this is the float chamber, and so this is the float, and this is the height. So, this is the height, and that height if we give small h, so this is delta h. So, that is the height difference, and if we remove this part, okay. So, this is the height difference, okay. Then this is section BB, and this is section AA again. So, what we can write? We can write the equation, that is Pa by rho f into G plus Ca square by 2G equal to Pv by rho f into G plus Cv square by 2G plus delta H plus Hf, right. So, this is the frictional loss, and this is the static height difference, right. And we know that Ca is much less than Cv. So, from this equation we can write Cv square by 2 will be equal to P A minus P B, right, by rho f. If we just cancel G from all the terms in both sides, then we can write minus delta H in delta F. So, that is minus delta H plus H F into G, right. So, that we can write. Now, it is given that this is the pressure drop across the orifice. So, this is the pressure drop across the orifice accounting for these two effects, static height difference and frictional losses, and it is given, if we go back to the problem statement, that if the pressure drop across the fuel metering orifice is 25% of that at the venturi. So, at the venturi pressure drop is P A minus P B, and if the orifice is 25%, so I can write this is the pressure drop across the orifice meter, okay, and that is given, that is only. So, this quantity is 0.25 of P A minus P B. So, that is given, right. So, if we write C B square, so we are getting C B square by 2 equal to P A minus P B by rho f, okay. And if we go back to the previous slide, so this is 25% of the P A minus P B divided by rho f. So, this is what is given, and then if we can write it. So, the pressure drop across the fuel metering orifice is we can write now delta H into G. So, what we can write? We can write it minus 0.25 into P A minus P B divided by rho f. Let me tell you, this delta H is, it can be written rho f into G into delta H divided by G into delta H, that would be written rho f, right. So, if we go back to the previous slide, so delta H into G, that can be written like this, and H f into G, and so this is an H f into G. So, basically it can be written that rho f into G into H f divided by rho f. So, the total pressure drop, this plus this, is equal to 25% of that at the venturi. So, you know that rho f into G into H minus plus rho f into G into H f by rho f, that is equal to. So, basically this G into delta H plus H f into G, that equal to rho f into G into delta H plus rho f into G into H f divided by rho f. So, this is 25% of the P A minus P B by rho f, that is given. So, from there we can calculate. So, this is 75 into P A minus P B divided by rho f. So, we can calculate what would be C B. Again let me write first. So, it is 2 into 0.75 into 0.1 minus 0.0925 megapascal into 10 power 6, we are converting to the Pascal, divided by 740 kg per meter cube. So, we will be getting, that is 3.9 meter per second if we calculate it. So, now this Cv is the velocity of fuel, right. So, velocity of fuel, at the orifice at section BB. So, once we know this Cv, what we can do? We can write mass flow rate of fuel that is again actual mass flow rate. So, m dot f actual, that is 0.45 minute per kg per minute. So, this is kg per second. So, this is kg per second, that would be equal to rho f into Cv actual into A f. So, this is area of fuel metering orifice at section BB. So, now this is actual velocity, again let me tell you. So, this is what we can write. So, this would be equal to CDF into Cv ideal. So, now let me go back to the previous slide. The velocity that we have calculated in the following this expression is again the ideal velocity, because when there is a flow of fuel through this particular arrangement, you know that this is sudden contraction. Also, we did not take the effect of surface tension into account. We did not consider the losses due to sudden contraction. Maybe we have considered the losses due to friction, but these two effects we did not consider. So, the velocity that we have here is the ideal velocity of fuel at the orifice at section BB. Okay. So, if we multiply with coefficient of discharge, that is the for fuel, then we can get the actual velocity. So, from this expression let me write. So, 0.45 divided by 60 equal to 740 I guess. So, this is rho f is given 740 kg per meter cube into 0.6 into 3.9 into pi by 4, this is df square. So, this df is the diameter of nozzle in this is diameter of the nozzle, diameter or of the fuel orifice meter, diameter of the fuel orifice. So, this is again straightforward. If we calculate, df is coming 2.35 millimeter. So, this is the last answer. Okay. So, you know that in the last class we had discussed about the calculation procedure of calculating the mass flow rate of air and mass flow rate of fuel. We had discussed several issues involved with this particular task, that is the calculation procedure. Today we had solved one problem, and this particular this problem will help us to understand the phenomenon in a better way. So, to summarize today's discussion, we have discussed about the limitations of a simple float type or an elementary carburetor. Identifying those, we have discussed that a designer should consider all these issues for the design of a modern carburetor. Then we have solved one numerical problem for the calculation of stoichiometric air fuel ratio considering a generic formula of fuel, and lastly we have solved another problem wherein we could we could solve the problem in such a way that knowing the mass flow rate of fuel and air, we could calculate the diameter of venturi at section BB and also the fuel orifice diameter for a flow of certain quantity of fuel for a given pressure drop. So, with this I stop here today and we shall continue our discussion in the next class. Thank you.